Hello everyone, and welcome to a discussion of Newton's second law problems with angles. With an angle. So I'm going to do this problem by doing an example with you, okay, and working it through in all of its symbolic glory. You'll notice that the only number I've given you in the problem set up here is the angle. Right? And even there, I could have just called it theta if I wanted to be really generic. Okay, and otherwise, you can just kind of do these in numbers, but I'm going to write this out symbolically. Do you have to be able to write this out symbolically? Not really, not in honors, although in AP, you definitely need to be able to work symbolically, so if you're thinking about taking an AP class in physics, you probably ought to practice. But if you can, right, try to take it into that next level of mathematics, that next level of physics sophistication, right, by working symbolically, if you can. If you don't want to, you can always find all the pieces and parts off to the side. And in fact, we're going to do a couple of Google quizzes where that's going to kind of be the way to do things. And it's going to kind of lead you through finding this piece, then this piece, then this piece, then this piece, and then in the end, you'll find the acceleration just like in this problem. So, let's work through this problem. We've got a box, generic box of mass m. It is being pulled across a rough horizontal floor with an applied force F of A at 35 degrees. See, there it goes. So notice it is accelerating. The coefficient of kinetic friction between the box and the ground is mu sub k, so that means there is some friction. What is the acceleration of the box? Well, I'm going to do this in parts, okay? So rather than just trying to answer this question in one big piece here, and I'm going to ask some intermediate questions to help us find some things out, okay? But the first thing we're going to do before we even go to find those pieces is draw a good force diagram. Right? Drawing a good force diagram is really setting up the physics. It's hard to do these problems without a good force diagram to help you along the way, whether it's asked for or not. So, as always, if we have a force that acts at an angle, we will draw that first, and we do in this case. Right? We've got F of A, which is at 35 degrees. And when we have a force that is not right along an axis, what do? We break it up into perpendicular components. So this is how much of F of A acts horizontally. That's F of AX. And this is how much of F of A acts vertically. This is F of AY. Note, these are perpendicular components, hence they are drawn head to tail. Please remember, this is a vector diagram, and you are drawing arrows. Well, what other forces act on the box? Well, gravity, of course, acting down. Right? F of G equals mg, of course. And the box is being supported by the surface, so there is a normal force which acts perpendicular to the surfaces, which in this case is up. Well, now our question becomes, though, how big should I draw that F of n force, that normal force? How long should I draw this arrow? Well, first off, notice here that in this case, the normal force is vertical. How many vertical forces do you see? I see 3. F of n, F of g, and F of ay, right? The vertical part of F of a. Is the box accelerating vertically? Well, it was accelerating, right? But it was accelerating horizontally. It's not even moving vertically up and down, right? So since the box is not accelerating vertically, what does that tell you about the forces? They must balance. So our two upward vertical forces, F of n and F of ay, have to balance out F of g. This will be something we'll revisit in a moment when we're trying to figure out the normal force. Everybody okay with that one? So note, we have 3 vertical forces to keep track of. There is one more force that acts, and that is the aforementioned kinetic friction. Friction, of course, acts parallel to surfaces and opposes motion. So since the box is being pulled to the right, friction will act to the left. How much friction do we have? Well, in this case, the box is accelerating horizontally. Right? It's accelerating to the right, as we saw. And so that means F of AX has to be bigger than F of FK, which is how I drew the diagram. Do you see all of the physics that is really involved in drawing a good force diagram? And if you draw a good force diagram, the rest of the problem is just math. Not easy, right? There's a lot going on, but it's still just math. If you spend the time to draw a good force diagram, you are really thinking through what forces balance, what don't, what interactions are going on. All of that is in the force diagram. Did I tell you you should probably draw a force diagram? You probably should. So, along our way to finding the acceleration, the first thing I want to know is an expression for the normal force. We've kind of almost done that, right? We said that it's not accelerating vertically, therefore the three vertical forces have to balance. So F of n and F of ay are upward, and they have to balance the downward force of gravity. So one step of algebra gets us to F of n equals F of g minus F of ay. But this isn't really broken down as much as it can be. We weren't given the force of gravity of the box. I could have said a box weighing something, W or F of g, right? But I gave you the mass of the box. But of course, we know, I hope by this point, that F of g can be written as mg. The force of gravity, or weight of the box, is its mass times the local gravitational field strength, which can be plugged in right there. F of ay can be rewritten in terms of the applied force and the angle. If we look at our little right triangle vector diagram we have right here, F of ay is the opposite side to the angle. F of a is the hypotenuse, hence we will use the sine function. So F of ay can be written as hypotenuse sine of 35 degrees. Now, if you need to write out another step, if you need to write sine is opposite over hypotenuse, F of ay over F of a, and then solve, by all means, go ahead. If you're so good at trig that you see this without writing anything out, by all means, skip this step and just substitute everything in. Right? Like, if you wrote this and then wrote that, I'd be happy with that. In APC, we kind of do a lot of that, right? Where we very quickly step through things. But in here, you write as many steps as you need. It's never bad to write more out. Okay? So this now is the normal force. So that's step one, leading up to, remember here, the acceleration of the box. Next thing we need to find is an expression for friction. This is going to factor into how much the box accelerates horizontally, right? But we can do that fairly quickly because remember that after our friction lab, we now know that the force of kinetic friction is given by the coefficient of kinetic friction, mu sub k, times the normal force. And we have an expression for the normal force right there. So we just multiply it by mu. And yes, you could factor this mu or distribute it in if you wanted, but you could also just leave it like this. Hey, it's a big equation, but, you know, that's what it is. Certainly if you were given numbers, you could just do the numbers. So now that we have friction, now we can figure out the acceleration of the box. How are we going to do that? Well, it's accelerating horizontally, so we're going to look at Newton's second law for the horizontal forces. Remember that Newton's second law is, of course, net force is mass times acceleration. So horizontally, what is the net force? Well, check out the force diagram. How many horizontal forces do you see? I see two. I see friction, and I see the horizontal component of the applied force, F of AX. Well, they're pointing in opposite directions, so that means we have to subtract them. But which one do we subtract from which one? Well, again, look at your force diagram. In a conventional coordinate system, F of AX, which is pointing to the right, would be positive. F of FK, which is pointing to the left, would be negative. So if we want to follow the conventional coordinate system where to the right and up are positive and to the left and down are negative, we would write the net force as F of AX minus F of FK. Do you notice here how I took the arrows off of the forces? Because I put in the directions explicitly. I said this one was positive. Of course, you don't have to write a positive there. And this one is negative. Really, we did vector addition, but we put in the directions. Okay? And that equals mass times acceleration. So we know net force is mass times acceleration, but in this case, net force is also F of AX minus F of FK. Well, we've already got a big expression for F of FK up here. But we do need to find, so if we solve for the acceleration just by dividing by the mass, right, now we need to plug stuff in for f of fk up here and f of ax. Well, what can we do with f of ax? Well, it is the adjacent side to this angle, where f of a is the hypotenuse. So we would use the cosine function. So f of ax would be f of a cosine of 35 degrees. Again, if needed, write out an extra step. That would get plugged in right there. This will get plugged in right there. And there it is. Right, there it is in all of its beautiful symbolic glory. About the only way I could have made this more symbolic would have been to call the angle theta. But I figured I had to give it a number just so we could draw the actual picture, right, the vector diagram. But I could have just called it theta or something like that. But this is it, right? That's not easy. That's not a simple little looking equation. And it's not one that you memorize. It's one that you know how to get it, right? So that you can apply it to a situation. If we're applying Newton's second law here, F net equals mass times acceleration. And we applied vertically Newton's first law, that when it's not accelerating vertically, the net force was 0, so the vertical forces had to balance. Right? We applied Newton's first law and Newton's second law here. But yeah, there's a lot of complications along the way. Draw the force diagram to help you see the trig and to see the forces that are occurring. And that will help you hopefully do this. Write out as many steps as you want, right, to be able to get it all written out in the end. And yeah, if I gave you numbers, you could easily figure out what this is. Figure out f of ax, figure out f of ay, figure out the weight, figure out friction, and plug numbers in, right, and come up with the acceleration. Do all your work off to the side. That's okay. But if you want to take it to that next level of sophistication, see if you can't write things out symbolically when you're working them through. You'll see me do this, of course, in my keys, and then put numbers in the last step. So we're closing in here on the end of this Newton's second law unit. We just have a couple more complications to throw in. But this is a good example to look back at when you're dealing with Newton's second law and angles.